we're doing a series of reactions from aluminum cans. So we're looking at aluminum. We're going to be getting the aluminum from literally aluminum cans, from soda cans. Now, aluminum does undergo redox reactions with both acid and base. We're going to be dealing with what happens, but I want you to think first. Soda, I've actually tested the pH of soda and it's down in the pH 3 range, so it's really, really acidic, bad for your teeth. It's not just the sugar that's bad for your teeth, but anyway, it's very acidic. And yet aluminum reacts with acid to form gas and aqueous aluminum. So wait a minute, what does that mean? That means that aluminum dissolves, okay? It reacts with acid. So how do we compensate for that? With soda cans or beer cans, both very acidic. We compensate for that by putting a very fine, thin polymer coating inside the can, which resists any sort of chemical reaction. Okay? Not only that, but we put it on the outside too, and it's a slightly different composition. We put it on the outside to keep the paint that is, or the stain that's on the aluminum that labels what you're about to drink, keep it from scratching off. So anyway, just keep that in mind. That's why we don't tend to eat acidic food out of aluminum cans past the due date, because what's happening is slowly that polymer is breaking down, and you can get aluminum in your food. That being said, consumption of a lot of aluminum or physical contact with a lot of aluminum through like aluminum-based antiperspirants is not healthy for you. Anyway, now I'm done my public service announcement, time to get to lab. So it undergoes various redox reactions with both acid and base. Now, you've done redox reactions. You did them last week in lab. You've already done them in class. So I'm going to take nitric acid, a strong acid, we know that, and I'm going to figure out what happens. Well, aluminum is oxidized in the half reaction to aluminum 3+, and in the process releases 3 electrons. Of course, I don't have white chalk, which is there it is. At the same time, the hydrogen, the acidic proton from the acid, reacts with those electrons, takes those electrons, and forms hydrogen gas, bubbly stuff, okay? Now, of course, we don't have an equal number of electrons that are being released and taken on, so we have to balance the reactions. Our net ionic reaction therefore comes out to be aluminum plus those 2 aluminums plus 6 acidic protons gives us 3 hydrogen gas and aqueous aluminum. As I said, it also reacts with base. Now this is also a redox reaction, but it's a little bit more complicated, so we're not going to break it down. But again, we take solid aluminum, we're taking a strong base, potassium hydroxide, and when we react the 2 of these together, we get potassium aluminate, and hydrogen gas. All right, now, one of the things we're going to be doing today is we're going to be making potassium aluminum sulfate dodecahydrate. Isn't that fun to say? Let's all say that together. Never mind. It's called alum. Okay? It's called alum because long before they knew what it was, they found that alum was helpful slightly medicinally. It also preserved pickles, kept them nice and crunchy. It also is used in baking powder. Okay, so it actually, that production of When this is reacted with acid, it produces hydrogen gas. It allows, and other things, it allows for the puffing up, the leavening of various substances that you're baking. So alum was discovered long before we knew what it actually was. So they named it alum. That's what we call it, because it's a lot faster than saying potassium aluminum sulfate dodecahydrate. So how do we make alum? Well, after we have made this potassium aluminate, we react the potassium aluminate with acid. And do we add water? No, the acid is already aqueous, okay? But the reaction itself includes water. Once we have the potassium aluminate, sulfuric acid, and the water reacting, there is our alum. And we have some aqueous K2SO4 potassium sulfate left over. So this is solid. So not only are we just going to do our first synthesis, which is cool, and see that aluminum reacts with both acid and base in redox reactions, we're also going to make some of this and do stoichiometry. Yay, my favorite. You can ask any of my prior students. Stoichiometry is like awesome. It's math with chemistry. All right, so we're going to start our stoichiometry. We're going to use stoichiometry pretty much the rest of the year. What we're going to be doing is massing our aluminum and then doing a whole bunch of reactions, getting alum, drying it out, and massing it. From the mass of aluminum, we can calculate our theoretical yield. Now remember, theoretical yield is the maximum amount of product you can get based on the starting material and your stoichiometric relationships, okay? Or, in other words, the maximum product you can get in a perfect world on a perfect day with a perfect chemist, okay? So we're going to be able to find the theoretical yield. When we mass the alum we make, we find the actual yield. And using the two of these, we can find our percent yield, which is how good you've done. It's also the efficiency. Remembering that our percent yield equation is actual minus theoretical. Now this has absolute value bars around it, which means you don't have a negative. Divide it by the theoretical yield and multiply it by 100%. All right, so the last little bit of this talk is just reminding you how to do a theoretical yield. In order to do a theoretical yield, you have to use the box. You have to go from the substance, the mass of it, to its moles using the molar mass. Then you go from moles of your starting material to moles of your product using the molar ratio. Then from moles of the product back to mass using the molar mass. So let's check it out. Here we've got aluminum. This is our first equation over there. 2 aluminums plus 6 potassium hydroxides give us 2 potassium aluminates. So I need to get aluminum to moles of aluminum, mass of aluminum to moles of aluminum. I use my molar mass. Now I, in theory, have the moles of aluminum. In order to get to moles of potassium aluminate, I use my molar ratio. So I have my moles of potassium aluminate over moles of aluminum. And I check out my stoichiometric coefficients, and it's 2 and 2. Unlike what you've done so far, this is a 2-step reaction. So what now happens is that potassium aluminate is reacted further. So I have to do this molar ratio, and then I have to do the molar ratio where I start with potassium aluminate and and with alum. So now I have my moles of potassium aluminate. I'm not going to be massing this, so I go straight from that to my molar ratio here, where I have moles, and I'm going to abbreviate it as alum, over moles of potassium aluminate. And you can see that's a 1-to-1 molar ratio. Finally, I'm going to take that moles of alum and convert it back to grams using its molar mass. So let's do an example of this. I'm going to take, let's find a place to do this. I'm going to start with, you're supposed to be starting with about 0.3 grams of aluminum, but you're going to be massing this on the analytical balance, so 4 decimal places. So I'm going to start with 0.3257 grams of aluminum. Now, first I have to get this into moles of aluminum. So 1 mole over 26.98 grams of aluminum. You can look that up on any periodic table. My grams of aluminum cancel. I'm going to need more space. Now I'm going to do my first molar ratio. 2 moles of potassium aluminate per 2 moles of aluminum. And my moles of aluminum cancel. Now I'm moving on to my second molar ratio. So 1 mole of alum per 1 mole of potassium aluminate. My moles of potassium aluminate cancel. Finally, I'm now way over here at moles of alum, so I need to get back to grams of alum because I can't mass moles of alum. So 474.38 grams of alum per mole of alum. And my moles of alum cancel. This is nothing but a lot of dimensional analysis. And when I plug this all in, I'm going to end up with 5.727 grams of alum. And that's my theoretical yield. Say I did this in lab, and I got in lab a mass of 2.7956 grams, so that was my actual yield. I could find my percent yield from that. Oops. Remember, this is an absolute value bar, not a 12. Okay, so that's what we're going to be doing today. We're going to be observing some chemical reactions with aluminum. Those will be done up front. You're going to be figuring out their chemical equations. Then you're going to be making alum and doing some stoichiometry. So that's what's on your docket for this week. Be careful and have fun.